Now we are going to derive another very important equation, Lagrange's equation. Before deriving Lagrange's equation, we have to know some more things. I will explain. First one is system point. Second one, configuration space. Third one, Hamilton's principle. And lastly, Lagrange's equation. These are the things we are going to study now. Consider a single point, a single particle within a system, and in order to describe the particle, we require three coordinates: x coordinate, y coordinate and z coordinate. And if within a system there are two particles, we require 6 coordinates to describe the system: x1, y1, z1 and x2, y2, z2. Therefore, the system with the two particles can be considered as a single system. There is a system with two particles and it can be considered as a single system with 6 coordinates. Therefore, this single system is called system point, a single system point with 3 coordinates. Or we say that the system point is existing in a 6-dimensional space. It is not 6 coordinates, it exists in a 6-dimensional space. Therefore, system point exists in a 6-dimensional space, and if instead of 2 points there are so many points, if there are n number of points, it can be considered as a system point, a single point, a system point which is situated in a 3n, there are total 3n number of coordinates, therefore it exists in a 3n dimensional space. If there are n number of particles, then the n numbered particle system can be considered as a single system, a system point which is existing in a 3n dimensional space. Okay. And that 3n dimensional space is called configuration space. That 3n dimensional space is called configuration space. There is no relation with the ordinary 3-dimensional space. It is another concept. And now we are going to study Hamilton's principle. Hamilton's principle states that an integral I is equal to integral from t1 to t2 t minus v dt. This integral is in a configuration space. The integral from t1 to t2, t capital T means kinetic energy, capital V means potential energy. T minus v dt is a constant. This is the Hamilton's principle. This is a constant, or it is called, it is an extremum. Extremum, it is maximum or it is minimum. Therefore, there is no, if it is a constant, the variation is equal to, change is equal to 0. That is delta I is equal to delta integral from t1 to t2 t minus v dt is equal to 0. This is the expression of Hamilton's principle. Now we are going to derive the very famous equation, Lagrange's equation, from Hamilton's principle. We can derive Lagrange's equation by means of some other ways also. Now here we are going to derive Lagrange's equation from Hamilton's principle. The importance of Lagrange's equation that we have already said in the first class itself, that in Lagrange's formulation we are using kinetic energy and potential energy, both are scalar quantities. In the case of Newtonian mechanics, we are using force, which is a vector quantity. Therefore, we are replacing the vector quantities by means of scalar quantities. Therefore, in Lagrangian formulation, we are using T and V, both are scalars. Therefore, it is easy than Newtonian formulation. Now we are going to derive Lagrange's equation. According to Hamilton's principle, this is the statement. Now, T is the kinetic energy. Kinetic energy is a function of Qj and Qj dot. Kinetic energy usually expressed as half mv square. It is a function of velocity, and hence it is a function of displacement position also. Therefore, it is a function of both Qj and Qj dot. But potential energy usually expressed as mgh. Therefore, it is a function of Qj alone. It is independent of Qj dot. Therefore, we can write, for a system with n number of particles, we can write the equation as delta I is equal to integral from t1 to t2 sigma j dot T by dot Qj into delta Qj plus dot T by dot Qj dot into delta Qj dot minus dou V by dou Qj into delta Qj into dt is equal to 0. Okay. Now, this is equal to integral from t1 to t2. The first and third terms can be combined. That is dou by dou Qj of t minus v into delta Qj. Similarly, delta Qj dt plus we can write integral from t1 to t2 dou by dou Qj dot of here t only. But what happens if we add minus v also here? Minus v means dou v by dou Qj dot. What is dou v by dou Qj dot? Dou v by dou Qj dot is equal to 0 because v is a function of Qj alone. It is independent of Qj dot. Therefore, if we add or subtract here dou v by dou Qj dot, there is no change. Therefore, here we can write in the similar fashion we can write t minus v delta Qj dot dt. Now, this thing we can consider later. Now, we are writing only the previous equation, this much only. And in this equation number 1, we consider the second term, that is integral from t1 to t2 dou by dou Qj of t delta Qj dot into dt. That is equal to integral from t1 to t2. We are considering the second term of this equation. This is equal to 0. This equation number 1, that is dot t by dou Qj dot into delta Qj dot can be written as d by dx of delta Qj into dt. Now, we can integrate the expression by parts. That is, first function dot t by dou Qj dot into derivative of the second. Derivative of the second means delta Qj within the limits t1 to t2 minus integral of derivative of the first, that is d by dx of dot t by dou Qj dot into integral of second. Dot t of, with respect to t we are integrating dou by d by dt of dou t by dou Qj dot into integral of second means delta Qj into dt. Now, here the variation in Qj from at the two endpoints is equal to 0. At the endpoints Qj is constant. At the lower limit and upper limit Qj is constant. Therefore, there is no variation for Qj at the two endpoints. Therefore, this term cancels. Therefore, the second term reduces to this one minus integral from t1 to t2 d by dt of this term. So, we can write sigma j. Here sigma j is there. Sigma j integral from t1 to t2 d by dt of dot t by dou Qj dot. Here we can write the negative sign along with this. Next step we can write delta Qj dt. Now, in this equation, instead of dou by dou Qj dot, we can write dou by dou Qj dot of t. We can write dou by dou Qj dot of t minus v. There is no change because dou v by dou Qj dot is equal to 0. That is, this equation becomes sigma j integral from t1 to t2. We are clubbing all these equations. Dou by dou Qj dot j of t minus v delta Qj plus d by dt of dou by dou Qj dot of t minus v delta Qj into dt. Now, here we can write T minus V is equal to L. T minus V is equal to L, where L is the Lagrangian. L is equal to T minus V. Kinetic energy minus potential energy. Therefore, this is equal to sigma j integral from T1 to T2 dou by dou. This term we can write first. That is d by dt of dou by dou q j dot of L. Here it is negative. This term is negative. That is, we have integrated by parts, and the first term is vanishes, second term is negative. That is why it is negative. D by dt of dou L by dou q j dot. This term is negative. Delta qj. That also can be taken last. Minus, or we can write in the same manner. That is equal to sigma j integral from T1 to T2 dou by dou qj of L minus d by dt of dou by dou qj dot of L into delta qj dt. Is equal to 0. Since it is equal to 0, we can the term inside the bracket also vanishes separately. That is dou L by dou qj minus d by dt of dou L by dou qj dot is equal to 0. Or we can write this term can be taken first, this term can be taken second. Both are same. That is d by dt of dou L by dou qj dot minus dou L by dou qj is equal to 0, where j is equal to 1, 2, 3, 4, etc. This is the Lagrange's equation. This is Lagrange's equation. Either we can write in this manner or this manner. D by dt of dou L by dou qj dot minus dou L by dou qj is equal to 0. This is same as that of Euler-Lagrange's equation. In Euler-Lagrange's equation, here it is d by dx, here it is d by dt. That is the only difference to see, where j is equal to 1, 2, 3, etc. This is a very important expression. It is very much used to solve problems in mechanics. This is the basic equation of, this is the second order differential equation of Lagrange's equation, and this is the basic equation to solve problems in mechanics in Lagrangian formulation. And the importance of Lagrangian formulation is that we have already said that here L is T minus V. The only quantity we are using here is L, that is equal to kinetic energy minus potential energy. There is a function, there is a scalar quantity, and as it is a scalar quantity, it is easy to solve using a problem, a complicated problem. Therefore, it is much better to apply Lagrange's equation compared to that of Newtonian equations and Newtonian mechanics. Okay.